Hello everyone, I'm Sudha, working as an Associate Professor of Chemistry in Nalla Narasimha Reddy Engineering College. I'm going to explain about spectrochemical series, which is one of the topic in the crystal field splitting in octahedral complexes. So in one of my lectures, I've explained about the crystal field splitting in an octahedral complex, where the metal atom is surrounded by 6 ligands and all the 6 ligands approach the central metal along the coordinate axis. So the Eg orbitals of the metal atom will affect more. That means they are repelled more by the ligands compared to the T2G orbitals of the metal atom. T2G orbitals include dxy, dyz and dzx. Eg orbitals include dx square minus y square and dz square. So as the ligands approach the metal atom, the degenerate d orbitals split into two sets of different energies. So in case of an octahedral complex, the Eg orbital energy will increase, whereas the energy of T2G orbitals decreases, because Eg orbitals will repel more by the ligand field than the T2G ligand. So that difference in energy between Eg and T2G set of orbitals after filling up of the electrons in the metal atom is called crystal field splitting energy. The difference in energy obtained after the filling up of the electrons in Eg and T2G set of orbitals is called as crystal field splitting energy, and that is represented by delta. So here delta O represents the crystal field splitting in an octahedral complex. So this crystal field splitting in an octahedral complex is different for number of complexes, and that depends mainly upon the nature of the ligands. So it is found experimentally, it is observed that the crystal field splitting energy in an octahedral complex for a number of complexes depends on the nature of the ligands. For example, for all the halide ions like fluoride, chloride, bromide and iodide, the delta O, the value of delta O is found to decrease as the size of the donor atom increases. So these are the donor atoms. As these attach to the metal atom, these are called donor atoms. So for all these ligands, though all are halide ions, but the value of delta O is found to decrease as the size of the donor atom increases. So we know that the atomic size increases top to bottom in a group. So if we consider the crystal field splitting values of halide complexes, it is generally in the order fluoride greater than, chloride greater than, bromide greater than, iodide. Because of the small size of fluoride ion, this interact more strongly with the d orbitals of the central metal atom. So the fluoride complexes give more crystal field splitting energy values. So greater the CFSE value, greater is the stability of the complex. So among all the halide ions, fluoride ion will give the higher CFSE values. So these fluoride complexes are more stable than the other halide complexes. Similarly, for a neutral ligands, that means where the ligands do not carry any charge. So if the lone pair present on the neutral ligand is highly localized on one particular atom, then such ligand results in higher CFSE values. So one example is ammonia, where the lone pair of electrons is highly localized on the nitrogen atom. So this ammonia results in the higher CFSE values. So these are some of the examples of how the ligands affects the crystal field splitting values of different complexes. So this is the experimentally observed order of different ligands, which is known as spectrochemical series. So number of ligands are arranged in the order of their crystal field splitting values. So some the ligands which are arranged on the left hand side of the spectrochemical series are called as weak field ligands, like iodide, bromide, sulfide, thiocyanate ion, chloride ion, and so on. Whereas the ligands that are arranged in the center of this spectrochemical series are called intermediate field ligands. So again, these ligands, they may result in higher CFSE values or they may result in lower CFSE values. Again, that depends upon the nature of the metal ion, the oxidation state of the metal, the size of the metal, and etc. So whereas the ligands that are arranged on the right hand side of the series are very strong field ligands, like nitrate ion, triphenylphosphine, and cyanide ion, carbon monoxide. These are strong field ligands. So weak field ligands produce high spin or spin free complexes, and they contain more number of unpaired electrons, whereas strong field ligands produce low spin or spin paired complexes. They contain less number of unpaired electrons. Similarly, weak field ligand complexes are strongly paramagnetic because they contain more number of unpaired electrons, whereas strong field ligand complexes are weakly paramagnetic or diamagnetic in nature. That means they do not exhibit any color, right? Because they contain less number of unpaired electrons. So this is about the spectrochemical series where the ligands are arranged in an order of their increasing crystal field splitting energy values.